We are now going to talk about Ampere's law, and it is the second milestone in our course. The first one is about Gauss' law for electric field, and this is the second law. Later on in the 6th week, we realized that Maxwell compiled all these laws and then showed that there exist electromagnetic waves. So the first one is Gauss' law for electric field. The second main equation is Ampere's law. And in this lecture, we are going to talk about Ampere's law. Our objectives will be to be able to state and understand each term mathematically and in words of Ampere's law. Then we are going to apply Ampere's law to solve some few problems. A quick recap of what we've learned so far and a previous knowledge that will help us in this video lecture. We've learned in previous videos that magnetic fields are produced by moving charges, and moving charges constitute current. So indeed, electric charges moving or current create magnetic field. And magnetic fields encircle the current. If it's a charge, then the magnetic field encircle around the charge as it moves. Then also, we came to appreciate that the magnetic field lines are always in closed loops. This is a direct consequence of Gauss' law for magnetic field. Gauss' law for magnetic field. I've not been emphasizing on that, but if you look in the handout, you see Gauss' law for magnetic field. Unlike electric charges where, electric charges where the electric field starts from the positive charges and terminates on the negative charges. Magnetic fields do not start from one point and end on another point. So we've been seeing these magnetic fields. You can see these ones, they always encircle around the current bearing element. So if you take this one, you see that they go around all the way and close up. The ones you can see have been terminated are indeed, we can't draw the whole loop, that's why it has been terminated like that. But indeed, it will go around all the way and then meet up. So they are always in closed loops. Yes, in this one too, this long wire too have magnetic field that is encircling it. It is in loops. These ones also, the ones you see as if they are terminated, they are not terminated. It's simply because we are not able to draw everything. That's why we leave it like that. If you come to a bar magnet, it is often drawn this way, as if it is starting from the North Pole and terminating at the South Pole. That is wrong. The correct way, the correct understanding you should have for a bar magnet is that the field lines continued through the bar itself. They don't terminate anywhere. They don't start anywhere and terminate. They are always in closed loops. Keep this point in mind. Now consider a current bearing wire creating magnetic fields. As you see now, we are showing two magnetic fields around this wire. There could be so many magnetic fields, but we are going to concentrate on one to explain Ampere's law. We take one magnetic field line and we divide it into very, very small segments. You can see very, very small segments, and here we are. We can have one here, another one, so many of them. Infinite number of small segments, and they add up to a closed magnetic field line. We've labeled just 4 of them. 1, 2, 3, 4. Just 4 of them. And each of them is a vector-like. So we divide the magnetic field path into infinitesimal length of them. Then for each length, we compute or we determine the magnetic field at that point and find the dot product between the magnetic field and the small elements. We find a dot product. So for this one alone, we find this dot product. And we continue to do the same thing for all of them. So we come to this side, the small element, the L. we find the magnetic field at that point, and we find the dot product. We do same for this segment, we do so for this segment, this segment, this segment, this segment, and we do so until we are able to determine the dot product for each small element of the closed path. Then we sum everything together. This symbol here tells us to sum everything together, and we are summing everything until we have a closed path. We do so for every small element until we close up the path. Is that okay? If we do this summation, we put everything together, we integrate. Indeed, if we are summing everything together, we say we are integrating over the closed path. If we succeed in adding every dot product of the path together, we call the value that we get magnetic line integral. Magnetic line integral. Ampere's law is telling us that if we are able to compute the magnetic line integral, it will be just as taking the enclosed current, the current within the wire, and multiplying it by the permittivity of free space. So if we are unable to calculate this, we can simply take up the current and then multiply it by the permittivity of free space, and it will be the same as doing that laborious job of finding the magnetic field and then the length of the wire and finding the dot product, and doing so for each small segment. A very important thing you should realize about this law is that it doesn't matter the radius of the magnetic field. If it is small, we can still divide it into small segments and find the magnetic field at each point, and then find the dot product at each point and add them together. It will be the same as doing it for the bigger circle. To be like doing so for the bigger circle. So it doesn't matter the radius of the magnetic field. Whatever you do, it will be equal to the current enclosed in it multiplied by the permittivity of free space. Now, let's take an example to explain what we are talking about. So here we are. We have 3 wires that are parallel to each other, and each wire is carrying current of different amounts. 2 amps here, 4.3 amps, then we have 1.8. What you need to take note of is that this current and that current are moving upwards, but for the middle one, it is coming downwards. Then the figure is also showing 3 different magnetic lines that are set up by the combination of these 3 wires. Line 1 consists of this line surrounding only this wire, and line 2 encloses the first current bearing wire and the second current bearing wire. Then the third one encloses everything all together. We are asked to determine the magnetic line integral for each path. We are expected to find the magnetic line integral for each path. I want to do what you consider as the most difficult one, and you will be able to do the easier one. So for the third path, it encloses all the 3 lines. So what we are going to do is to write the expression. We don't have the value of the magnetic field at each point. We don't have the small element at each point. So this one will just be a representation. We are not going to do any calculation here. But when we come here, we'll be able to get the currents that are enclosed within this path. If we sum them together, we can multiply it by the permittivity of free space, and that will represent the whole of this. So let's go. What is the enclosed current? The enclosed current consists of the current upwards here and the current upwards here. Because they are in the same direction, we add them together. That's 2.0 and 1.8. We add them together. And because 4.3 amps is in the opposite direction, we take it out. you could do it the other way around. If the current moving downwards is positive, then the others will be negative. The current moving upwards will be negative. And for what we are doing here, the enclosed current, the algebraic sum of all the currents, will add up to negative 0.5 amps. So that will be the enclosed current here. We multiply it by the permittivity of free space, and we get 2 pi by 10 to the negative 7 Tesla meter. That will be the line integral. The magnetic field multiplied by the length, Tesla meter. That's what we get here. Let's look at for the second part. The second part encloses the first wire and the third wire. Okay, so the first wire and the third wire. So what we need is to find the current enclosed. The current enclosed will be the algebraic sum of the two currents. They are all in the same direction, so we just add them up and we get 3.8 amps. Again, we multiply by the permittivity of free space and we get 4.8 by 10 to the power negative 6 Tesla meter. I want you to do the third one yourself. That's very easy, and I expect you to get 8 pi by 10 to the power negative 6 Tesla meter. Alright, that's all we have for Ampere's law. Let me just remind you what the law says, and that will be okay. So it says the magnetic line integral is equal to the current enclosed multiplied by the permittivity of free space. That's what Ampere's law tells us. Thank you.